Okay, hello everybody. So we're going to continue with binary search tree, and we talk about adding, searching, and traversing a binary search tree. And now we're going to talk about deleting. So again, the binary search tree has the properties that the left children should be less than each node and right children should be bigger. And so we need to maintain that every time we're removing and data from the binary search tree. So when you're trying to remove, there are different scenarios can happen. And so we're going to go through the scenarios first, and then we start writing a code for them. So the first scenario, we call it the case one, basically. And the case one is the case that the node that you're trying to remove it does not have any left children. So you can see that on the picture as well, right? So this node, for example, the node current, that's the node we're going to be removed from this list, sorry, from this tree. And then it doesn't have any left children. If that's the case, we call it a case number one. So again, the case number one is the case that you're trying to remove a node. So you have to first search for the node. You're finding that node, we call it current. And then the current node, it doesn't have any left children. If that's the case, we call it a case one. And that is going to be the simplest case. So that means the left child may or may not, the current node may or may not have the right subtree, but for sure it doesn't have any left child. So what we have to do is we're going to connect the right child, the right subtree, to the parent of this current node, and then we're going to basically remove that parent. So we're not really removing it by making it null or anything, because it's Java. The garbage collector is going to collect it, but nobody pointing to it. So the parent is no longer going to point to this. It's going to point to the left children if there is any. So then we just have to figure it out that this current was the parent dot left child or was the parent dot right child. So if it was a parent dot left, then we need to do the current dot right equal to, or parent dot left equal to the current dot right. Otherwise, we have to do parent dot. So it's again, it's either the left side or right. So if it's a left, so parent dot left is equal to current dot left, current dot right. Or if it's a right children of the parent, then parent dot right is equal to the current dot right. So the current dot right is always going to stay the same. The only thing is going to change is either the left side of the parent or is in the right side of the parent. So when we're trying to remove a node, we have to search for it, and then we find it, we need to keep track of the parent. So again, you need two runner when you need to remove a particular key or element from your list. You're searching for it and you find it, you need to know who's the father of it. And also you need to know if it's in the left side of its father or is in the right side of the father. And then you're going to get the, check if it does have any left children or not. If it doesn't have any children, so it's a very simple case. So you're just going to do the current dot right and assign it to the parent, either left or right. So that's case one. And again, it can have a, situation that the element that you're trying to remove is the left child of the parent or the right child of the parent. So it has basically case 1A and case 1B. We're going to see some example of it. So here, we're trying to, this is our basic tree, and we're trying to remove 10. Node 10. So when we start searching, again, we're always going to start from the root because we only have access to the root at the beginning. So we have to, do based on exactly like what we do in the search, right? So we're trying to first find the 10. So we're going to go to 20 and compare the 20 with 10. 20 is bigger than 10. That means 10 is going to be in the left side of the root. So we go to the left. And then we check the 10. And then it happened to be, comparison when you return 0, basically. They're going to be, we're finding it. So that's the element that we're trying to remove. Now we find the element, we find its father. If father was a root. Now we're going to check if the element does have any left child or not. It doesn't have any left child, so this is the case 1. So what I'm gonna have to do is I'm gonna tell the parent dot left to point to this current dot right. And so as you can see, that's become this new tree, and the element 10 got removed from the list. Now your question might be that, okay, now 16 is, it used to be in the level 3, like 0, 1, 2, right? So level 2. But now that we remove 10, is it still going to be in the level 3 or not? So based on this picture, it feels like it is staying in level 3, but in reality, no, it's going to move up, right? So it's going to go to the previous node, because now you only have one edge from the root to get to that. So that means it's going to be in one level up, right? So just want to clarify on the picture, because the picture doesn't really show that. So let's now go with another example. Like imagine we're trying to remove the another node from this list, and so that node is going to be the 27, or yeah, 27, for example. No, sorry. Let me see. Yeah, they're all going to be the left children. So all these examples. We're going to go up with another example that the element that you're trying to remove is going to be the right child. So you know, the 80 is the right child, 40 is the right child, but the problem with those are that they're going to have left children. Okay, 16 actually is a good one, right? So we're going to remove 16 from the list. So we have to search for it, right? So that's a different scenario. We're trying to remove 16 from this 3. So 16 is less than 20. We go to the left. 16 is bigger than 10. So we're going to go to the right. And 16 is equal to 16. So we find our node. So this become our current. 16 is our current node. And 10 is become our basically the parent of it. Now, is it a case 1 or 2? It is case 1, because we don't have any left children. So the case 2, obviously we do have left children, right? So it doesn't have any left children, so it's case 1. So how I'm going to remove it, I'm just going to tell the parent dot, now this time it's in the right side of the parent. So parent, which is 10, dot right is going to be equal to the current dot right. So the current dot right here is null, right? Because it doesn't have any right children. It doesn't have left children, but also it doesn't have any right children. So that means that the parent dot right also is going to become null. So basically 10 become a leaf node, right? It's not going. So 16 is going to be removed, and 10 is become the leaf node. So any other cases that you think might happen here? So let's think about, what if the element that we're trying to remove, it's going to be the root itself, right? So imagine we don't have the 10 and 16. So and then we're trying to remove 20. So if we're trying to remove 20, and imagine 20 doesn't, you know, have any 10, you know, any left children. So 10 and 16, we already removed them, for example. Imagine that's the case. So we look at the 20, and if we removed already the 10 and 16, then there's no left children. So it's going to become the case 1. Now I have to tell the father of it to point to its right children, which is 40. But that's root, and root doesn't have any father, right? So that means when I remove this, what is going to happen? 40 is going to become my root, right? So that's what is going to happen. So that's another case we have to take care of it. So it's, if the element that we're trying to remove is the root, and the root doesn't have any left children, then whoever is in the right side of our root become the basically head of this, so become the root. So those are the things we have to take care of it when we're writing the code for this part of the scenario, the case 1. Now let's look at the case 2. So obviously the case 2 is when we're trying to remove an element, and the element, it does have a left child. So how are we going to do that? Let's look at the picture. So I'm trying to remove the current, and current does have an entire left subtree. Not only one, it has the entire left subtree. It can be one or it can be more. So in order to maintain the property of binary search tree, and the fact that everything is in the left side should be smaller than the node. So what I have to do here in the left side, I need to go ahead and search for the most, basically, the smallest element in the left subtree here, the part that we're going to show you in the circle, right? So we have to go here and search for the smallest element. The smallest element here is going to be, sorry, actually not the smallest element. It's going to be the largest element, sorry, largest, because we were looking for the rightmost. So we're going to switch, right? So we're going to find the rightmost, which is going to be the biggest element in the left side of our subtree. And then we're going to swapping it with the element that we're trying to remove it. So that way we're making sure that the entire left subtree are going to be smaller than, because we're finding the most largest one and we put it in the top and we put it in instead of the current. So we're removing the current, but we're swapping it. Basically, we're not removing it, but just removing it. We're swapping it with the largest element in the right side of its left children or left subtree. So again, there are two steps that you have to keep that in mind. So we first finding an element that we're trying to remove it. We call it current. Then we need to see if it does have a left subtree or not. It does have a left subtree, case 2. Then from there, we're going into the left first. We first go into the left, and from there, we're searching for the most right. Right, so that's one of the steps that many students miss when they're trying to implement or they're trying to analyze the delete in the case 2. They're starting to search right here from the right child of the current. But there's one extra step here. You first have to go to the left part of your current, the element that you're trying to remove. Then from there, you're going to search for the most right. And when you find the most right, for sure the most right here is going to be the largest element in this subtree. So you can swap it. So here how we're searching for the most right elements. To search for the most right element, again, we need two runners. The rightmost and the parent of the rightmost. So we start from the current. So both of these elements are going to be current. And then we keep going all the way until we find the rightmost. So we keep going and going and going, and we're checking that if the element does have any right children. And we keep going until we get to the point that it's telling us that the element that we are on it doesn't have any right children anymore. It may have left children or not, we don't care. But for sure, it doesn't have any left children. That means that's the rightmost. We find it. So how we know we find the rightmost is by keep going recursively into the right side of our left subtree of the element that we're trying to remove. And if we find the element that doesn't have any right children, that is going to be our rightmost. And since we have two runners, the parent of the rightmost is already defined now. So it's going to be always one element behind, right? One node behind. So we find the parent, we find the most right. So we have to now swap the most right, take it off from here and put it on top of instead of the current. So now my current become the rightmost element that I had here. And that means I removed it from the list. But then I have to do something with the left children. I know this rightmost doesn't have any right children for sure. That's why it's rightmost, but it may have left children. So what I have to do with the left children, right? So what I have to do is I'm going to tell the mother here, the parent of the most right, or the parent of rightmost, to now take care of the children of the left side of this rightmost, kid. So as you can see, the parent of the rightmost dot right is going to become equal to the rightmost dot left. So that way we're going to basically cover this and then we're going to get the most right, and we're going to put it on the top of there. So when we're going to put it on the top, that means we need to tell the parent of the current that you no longer are going to point to this current. You're going to point to the rightmost, right? So and that's again going to be parent that either left or right is going to be the rightmost, basically, or the basically the rightmost that we find. So we're copying it on the top of that. And that way we're making sure that we're maintaining the entire property, because we find the largest element where we swap it. So we know that since it's the largest element, it's going to be, you know, the largest one, and everything in the left side of our subtree now is going to be smaller than this. So we're not going to break any of the properties of our binary search tree. So let's look at some of the examples.